Okay, so now that you've learned about the binary number system, what can we do with just ones and zeros? Well, we can do what we can with any number system. We can add, subtract, multiply, divide, etc. But there are also some more basic operations that we can do with just a 1 or 0, an on or off, or true or false value. We can do what is known as Boolean algebra. And what is a Boolean? Well, a Boolean is a true or false value, and that was named after George Boole. There he is. See a picture of George over here. He was a English-born mathematician back in the 1800s, as you can see here on wonderful Wikipedia. And he's pretty much the father of digital logic, which is used in the modern digital computer. Pretty awesome. All right, so Boolean basics. You should have a handout on Polylearn that looks like this, and it talks about the 3 basic logic operations. What can you do with 2 values, a true and a false? Well, the first one is an AND operation. So it's saying if something is true and something else is true, then they're both true. So here we have something called a truth table. And the truth table shows we have inputs on the left, which are these x and y, and the output on the right, which here we're calling f. We're saying f is equal to x and y. And you notice this dot represents the AND symbol. So when you have 2 values, what are all the possible combinations? Well, to figure out how many, you always take 2 to the number of inputs. So here we have 2 inputs, so 2 to the power of 2 is 4. We know we're going to have 4 possible combinations of inputs. Both inputs can be 0. Remember, since we're doing binary here, we can only have a 0 or a 1 for each input. X could be 0, Y could be 1, X could be 1, Y could be 0, or they both could be 1. So the AND operation shows you here that the only time the output f, x and y, is a 1 is when both of them are 1. So this is only true if both conditions x and y are true. You see everywhere else the output is 0. Alright, so that's the AND operation. Now if we move over to the OR, again we list all possible combinations, x, y, same choices here. Now in this case, we get a true output or a 1 output if x or y is either true or both. So here we have a y is a 1, so we have at least 1, 1, we get a 1. At least 1, 1, we get a 1. Both are 1, we get a 1. Otherwise, if there's nothing that's 1, we get a 0. So these can be extended to more than 2 inputs. For an OR operation, you have to have at least 1, 1 to get a 1. And for an AND operation, all of them have to be 1s to get a 1. Now we have the NOT operation. The NOT just means an inversion. So if we're inverting an input x of 0, the output is going to be the opposite of it. So the opposite of 0 is 1, the opposite of 1 is 0. So AND, OR, and NOT. These are the 3 basic Boolean operations that we do with binary numbers. Now, we can model these operations as what we call gates. So here you can see what the symbol for an AND gate, an OR gate, and an inverter looks like. So this is showing that this AND gate has 2 inputs. The inputs are on the left, and 1 output, and it has this half moon shape. So here you could put your input x and y and output f. Your OR gate looks like sort of the half moon shape, but with a curvy back. Again, this specific OR gate shows it has 2 inputs and 1 output. And then we have the inverter. The inverter is a triangle with this dot. That means a negation. And this inverter, or all inverters, show that you only have 1 input and it gets inverted to become the inverted output. So you'll see that we're going to be using these gates to draw some binary circuits. Now, when you might have taken a digital design class 10 years ago, as I did, you would have spent a lot of time going through Boolean algebra axioms. Now these are very useful to know, but I'm not going to go over these. I think you can look at this at your own time, and you can prove to yourself that anytime a 0 and a 0 is a 0, a 1 and a 1 is a 1, etc. And then you can look at anything ended with a 0 is a 0. Yeah, I'm not going to go over these. However, there is one axiom that I do want to go over, and that's this last row here, De Morgan's, because this will prove extremely useful in what we'll be doing in future classes. So De Morgan's law here is showing that the negation of x or y, so here you're seeing x or y all negated, the bar over it means the whole thing is negated. Another word for negated is inverted. And that equals x naught, so x inverted, and y inverted. So I'm going to walk through this axiom for you and show how to apply it to different equations. So let's pull up the Smart Notebook here. So again, we were saying that, got to pull up the pen. De Morgan's is saying that x, y, you don't always have to put the dot in the middle to show that they're ended. Negated is equal to x naught or y naught. The other way to write this is xy negated is equal to x naught or y naught. So sometimes you see the negation or the inversion shown as a bar, other times it's shown as a tick mark. Okay, so what this law is doing is you're changing the ands to an or. So the ands here are becoming an or. And you'll see why this proves useful, because you can change from one form of having a whole bunch of AND gates to having a whole bunch of OR gates. And sometimes it's beneficial to have one versus the other, because you want to create as small as possible circuit. And so in one form you might have fewer components than in another form. So let me just explain how this rule is applied to a bigger equation. So I'm going to pull up a new page here. Let's say we had this expression, A, B, C naught, or D, E naught. All of that knotted. Okay, so here this is something that's called an SOP form, which stands for sum of products. Why is it a sum of products? Because here we have one product. These are all ANDed together, also known as a logical multiply, and these are ANDed together. And then they're summed. So it's a sum of products. Now, if we translate this into, or if we use De Morgan's law, we're going to come up with a different form. Now, how you apply De Morgan's law is everything that was not negated becomes negated, and every AND becomes an OR. So here we're going to get A naught or B naught or C. So all of these ANDs here became the ORs, and the A that wasn't knotted became knotted, the B that wasn't knotted became knotted, and the C that was knotted is no longer knotted. Now this OR becomes an AND, and then we do the same over here. The D becomes a D naught, that AND becomes an OR, and the F becomes an F. So here we get A naught or B naught or C ANDed with D naught or F. Now we have a POS form, or product of sums.